So good evening, everyone. I am Arnesh. I'm a second year PhD student in the Department of Aerospace Engineering, IIT Kanpur. And I'll be taking today's tutorial session on computational science and engineering. And today, this is the second session of this series. And we will be discussing on linear algebra. We'll be basically solving some problems. So let us begin. So the first problem will be finding eigenvalues and eigenvector for the given system. So the given system is this. So there is a matrix A and we will find its eigenvalues and eigenvectors. So as you have been taught in class that any matrix which is of the order m cross n, it can be a square matrix or a rectangular matrix. If it is multiplied by a vector n cross 1 and gives back the vector multiplied by scalar, then we will call it to be, this scalar will be called as an eigenvalue, and this vector, which is same as this vector, will be called as eigenvector. So this has been taught to you in class. So we'll be solving this problem. This is a very simple problem. So if this is the case, x is equal to lambda x, we have to solve for lambda. So if I just bring this to the left hand side, that is ax, this will become 0. If I just do this, that is I multiply lambda with an identity matrix and multiply this entire matrix, negate that matrix from A and then multiply that with that vector. So this two are equal. So if we want to find value of lambda for a general vector x, then the determinant of this matrix has to be 0. And if we put this determinant as 0, we will get the characteristics equation. So now let us find the determinant. So before we find the determinant, let us find this matrix. So if we just take the determinant, that will be you can do the multiplication on your own, and that will lead to this, which is equal to 0. Now let us solve for this. This will be equal to 0. So we will now take x minus 1 common from all these terms. This simple factorization which you might have done in your plus 2 level. If we'll take lambda minus 1 common from all these terms, again this term can be factorized, the term that is inside. So this will ultimately lead to if you just factorize this, we will get lambda minus 1, lambda minus 2. So this is a 4 cross 4 system, and as you have learned in class that a 4 cross 4 system has 4 eigenvalues. So the 4 eigenvalues of the system are, so 3 of them are same, that is 1, and 1 is 2. But nevertheless, these are 4 eigenvalues. Now we have to find eigenvectors. So the first one is, this won't be lambda 1, this will be just lambda. All of these are different values of lambda. So let us take the first case when lambda is equal to 2. So in this case, we will need to find the vector corresponding to lambda equal to 2. So if we again go back to the system, this was the system. Now we have to find a vector x, the eigenvector corresponding to lambda, which is equal to 2. So what we will do is we will solve this equation a minus 2i x, and the solution of this equation will give us the eigenvector corresponding to lambda equal to x, lambda equal to 2. So this is how we get the eigenvector. So for eigenvalue, we solved this equation. Determinant of a minus lambda equal to 0. And for eigenvector, we will solve this equation. This linear equation where we have to find the value of x. So there is a homogeneous equation and we have seen how to solve homogeneous equations. So this is the matrix where lambda is equal to 2. So if we put lambda equal to 2, we will get this as the vector. Now we will do simple row interpolation, which I have demonstrated to in the last class. So we will subtract the first row from fourth row and put that in fourth row. We will subtract the third row from the first row and put that in the third row, and subtract the second row from the first row and put that in the second row. So we will get this. Sorry, we will multiply this by 2. Next, what we will do is we'll add the third row with half of the second row and put them in second row. Now this is the upper triangular matrix. We have reduced the A minus 2i matrix to an upper triangular matrix, and now we can use back substitution as I have demonstrated to in last class to get the vector x. So this is the vector, we will find it out. Now let us multiply. So the fourth row will not give us anything because the fourth row has all the elements as 0. If we multiply with this vector, that will give us 0, and the right hand side is also 0. So this is consistent, but the fourth row will not give us anything. So we'll go to the third row. That will give us So we can get x3 in terms of x4. So x3 will be 3 by 2 into x4. We'll just make a box around it because we'll need it later on. Now we'll come to second row. So if we just do the multiplication, so I have made a mistake here, I'm sorry. This will be 3 by 2 x3 equal to x4. So x3 will be 2 by 3 into x4. Not the other way. So now if we solve this, we will get, we'll just put this in and we will get x2 equal to minus x4. We'll again box that. If we go to first row, what we will get is so we have replaced x3 with x4, this equation. We have replaced x2 equal to minus x4 with this, and with this we will get x1 in terms of x4. So if you see carefully, we have got three relations. So x3 depends on a value of x4, x2 depends on a value of x4, and x1 depends on a value of x4. What that means is that if we give a random value of x4, we will get a vector. So the eigenvector for this system of eigenvector for this matrix corresponding to the eigenvalue lambda equal to 2 will not be an unique vector. There can be infinitely many vectors like this, and that will depend upon the value of x4. But all of these vectors will be parallel. Depending upon the value of x4, these vectors will have different values, but these all will be parallel vectors. So let x4 is equal to minus 3. So then the eigenvector, we will write it as capital X corresponding to lambda equal to 2. That will be, so x4 we will put minus 3, and from previous relations we will have x3 equal to minus 2 by 3 x4, and if you can just put those in, you will get the values as this. So this is the eigenvector corresponding to the value lambda equal to 2. You can do similar exercise and find the eigenvector corresponding to lambda equal to 1 as. So you check this on your own. I think you should be able to do it. So this is how you solve for eigenvectors and eigenvalues for a given matrix. Well, now we will go to the next problem.
Excuse me, sir.
Yes, Jitendra.
Yes, sir. Sir, here we are solve the problem in that we have a three lambda is equal lambda 1, lambda 2, lambda 3 is equal to 1, and
Right.
lambda 4 is equal to I think 3. Correct?
Lambda 4, no, there is
2.
2.
I think 2.
Yes, yes,
Yeah.
right.
So, 3 lambda, lambda 1, lambda 2, lambda 3 are repetitive. So it is not called distinct. Am I right?
Right, right, you're right.
Yeah. So what can we say about this type of matrix when we are not getting distinct eigenvalue? And when we are getting a distinct eigenvalue, then what we can say? Or suppose any matrix is given, so can we say directly this matrix give the distinct eigenvalue, or this matrix cannot give the distinct eigenvalue? Suppose we get the distinct eigenvalue, then what happens with that matrix? Suppose we are not getting distinct eigenvalue, then what happens with that matrix?
Okay, okay, I'll tell you.
What about the eigenvectors? Can we justify about that?
Right, right, I'll tell you. I will tell you. So you see, Jitendra,
Yes.
we have seen a matrix can have 4 distinct eigenvalues, and a matrix can have 3 same eigenvalues, right? Now
Yes.
what will happen is, in this case, since it has 3 same eigenvalues,
Hmm.
so there will be, it has 2 independent eigenvalues, right? 1 and 2,
Yeah.
right? And
Yeah.
rest 2 are same. So I'll just go back. So before I tell you the answer, can you answer a question from my side? So this is a reduced matrix, right?
Yes. Yes.
See, what that means is it has 2 independent eigenvectors, right?
Yeah.
So this system will have independent eigenvectors, and the space can be spanned by these 2 vectors.
Okay.
Okay.
So the basis vector is only 2. Can we say
Right.
like that?
No, no, no.
Yeah.
So these two vectors will span, like, yes. So these 2 vectors will form the like span the basis, right?
Okay. Okay.
And if we have 4, then we will need all those 4, the linear combination of all those 4 vectors.
Okay.
Is that clear?
Uh, I'm clear, but not too much clear. But yes, I can understood. If a distinct eigenvalue, then how many distinct eigenvalue that will become the basis of the span? Correct. That will make a span. Correct.
See, there are
Understood that
4.
you can just,
If you
I want a general statement. A general statement is like that. Whatever you said, according to that, if I get the distinct value, then that distinct value, suppose 2 distinct value for lambda, then in the that means the space is span is 2. Suppose 3 distinct value, then span is 3. Okay, am I right? I understood like that. Am
Yes,
I correct? Understood?
yes, you are correct in this.
Okay, so that knowledge is useful. Suppose this type of question is asked in any competitive exam or any assignment or any interview type. At that time, I can use this knowledge.
Yes,
Correct?
you can use this much. Yes.
Okay, okay. So one more thing, sir. If you are not disturbed, then I would like to ask,
Yes, go ahead.
during the, yeah, yeah, during the lecture of sir, he explained you about some Fibonacci sequence, and he write F100 is equal to inverted V100 SC. I don't know what is the symbol inverted V. What we can say? I think this is the eigenvector matrix
Wait,
inverted VC, inverted V. Please,
I guess
sometimes
it's capital lambda.
wait.
can we say lambda?
Oh, so this inverted V. So
Yeah, yeah. What you can say about this?
so that is just a symbol. That's the symbol represents a diagonal matrix. That's it.
Yeah,
So
yeah,
that's a symbol. So the matrix is defined. So this is just like A, B, C or something D. The matrix corresponding to this symbol has been defined. So you can
okay. Right now, we say it is a diagonal matrix, correct?
right, right. I
Okay,
think
somewhere,
I
sir,
think
this matrix directly. So, can you explain me how to elaborate or evaluate that matrix? Somewhere, sir, write directly this matrix, but I can't understood how it will become.
see
Yes,
Jitendra, you are confusing two things. So you go
yes.
through that part of the lecture again. The
Uh,
the symbol means, I told you what the symbol means. Okay, as
Yes.
far as I remember, this is the so the matrix corresponding to this is the matrix of the eigenvectors. Sorry, the matrix of the eigenvalues as diagonal
Correct.
elements.
Yeah.
I think this was done in class. Okay,
Hmm.
so
Hmm.
I think this part I have been able to make it clear that this symbol has been given to make it a bit distinct. That's it. I think this
Hmm.
has come in the lecture where he was explaining singular value decomposition.
Yeah, 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 yeah.
Right,
That is also
right.
utilized
So,
there. Even Fibonacci sequence also it is utilized.
right, right. So the next part of your question, I'm not being able to understand. So the first, I told you about the symbol, right? The thing that you are speaking about symbol, I have told you that. You just tell me about the Fibonacci series.
Yeah,
Sorry, you just repeat your question. I'll tell you.
yeah. In Fibonacci sequence, sir, is write one step like this way. F100 is equal to that symbol to the power 100 into SC.
Okay, 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 okay. Right. So see, what it
Yeah.
says is F100.
Is equal to
Uh,
that symbol, right? That symbol to the power 100
this symbol to the power 100. Okay.
into C.
Right. Okay. So what this means is, so
Yes.
like suppose we will do an example, and I'll so the next example after this, I guess you will be able to understand it better.
Oh,
So
okay.
you just hold on to this answer, although this example is not about Fibonacci series, but I
Yes.
think you will be able to answer this, understand this,
And
what he was trying.
no problem, no problem, sir. Continue, please. Continue.
Okay.
Yeah,
So
yeah.
you just remember your question. Just stop me after this example and I'll explain it to you. Okay.
Yeah, sir. No problem, no problem.
So this is the next example. That will be so we have to diagonalize this matrix A, and we also have to find A raised to the power 8. So again, before we go on to diagonalize this, we have to find the eigenvalues and eigenvectors, and that will require us to find the characteristics equation, determinant of this as 0. So let us try to find the characteristics equation. So this is the characteristics equation, and if we just do simple factorization, we will be able to find this. So we have three distinct eigenvalues here: -1, 3, 4. So again, we will have three eigenvectors here. The first one corresponding to this. So I have shown you in the previous example how to find eigenvectors. I'm not showing that to you here. You can try them on your own. So the eigenvector corresponding to the eigenvalue lambda is equal to -1 will be -3, 1, 0. This can again be found by preliminary row column operations. The second eigenvector corresponding to the eigenvalue lambda equal to 3 will be 1, 1, minus 4. The third eigenvector corresponding to the eigenvalue 4 will be this is 0. So I'm not showing you how to do that here, but I have done that in the previous example and you can find this in similar way. So now we will make a matrix of eigenvectors. So we will just put these eigenvectors in order. So the matrix, this will be column 1, this will be column 2, and this will be column 3. This will be the matrix P. Now we have to find the inverse of this matrix. So in the last lecture, I have demonstrated to you how to find inverse. You can find an inverse of a matrix in many different ways. You can choose any one of them to solve for the inverse. I have done this here. I'm not showing here how to do this, but this will be the inverse of the given matrix. Now, what is the significance of diagonalization? So we will see that, but let's first diagonalize this matrix. So if we do the multiplication, we will get the, so first we'll multiply these two matrices. So this is the diagonal matrix. So if you see the lambda, the eigenvalues are -1, 3, 4. This matrix D has diagonal elements as the eigenvalues -1, 3, 4. Okay, and how does this help us? Jitendra,
Yes, sir. Yes, sir.
so I think similar thing was done in class, like in the lecture of Professor
Yes, sir.
Dev.
From this example, what I understood, just I want to tell it, yeah, am I correct or not? That's why I'm saying.
Okay.
Suppose any matrix is given to you and you want to find the diagonalization. So first find the eigenvalue, then find the eigenvector, respective eigenvector matrix you are finding like a P, then find the inverse of that, that is a P inverse, then
Huh.
multiply P inverse AP, then you are finding the diagonal matrix of A. Am I right?
Right. Right.
Yes. Okay. So that diagonal matrix we are finding. But in my question, what happens? Whatever that the symbol we are finding, in that we are getting a lambda 1, lambda 2 up to lambda n. So
Because that is a n cross n system. That's a general system.
yeah, now in this question, I have a question. I have a one doubt like this way. Suppose here the eigenvalue I am getting, that is a distinct eigenvalue. Okay, lambda 1, lambda 2, lambda 3 are not matched. But in the previous case, lambda 1, lambda 2, lambda 3 are same and lambda 4 are different. So in that case, what happens if I am trying to make a matrix like a P? So it is quite difficult to make. Am I right?
Why it is difficult to make?
Because I have a two vector only na.
Huh?
So see here what happens. I have three lambda 1 distinct value. Lambda 1 is not equal to
Right.
lambda 2
Right.
is,
Okay.
yeah,
See,
I
I
can
I,
easily
I
get P.
understand. You can make that matrix, but that is non-invertible. I understand
Not
your question.
yes,
That
yes, yes,
matrix is
yes.
non-invertible.
So can I conclude like this way? Suppose I have not distinct eigenvalue, then that matrix is not diagonalizable or not invertible. Am I right?
Right.
Okay, okay, okay. Thank you, sir. Okay. Now continue.
Okay.
Yeah.
So your doubt is cleared then? You understand why this is being done?
Yes, I understood this particular example. No problem.
Okay. So now what we will do is D is equal to P inverse AP, right? So
Yes.
let us multiply this with P on the left hand side. So what we will get is this. This will create an
Identity.
identity. So PD is AP. Next, what we do is multiply P inverse from the right hand side.
Yeah.
And matrix multiplication is non-commutative. So this
Yes.
is different. I think you. So again, this will become an identity and we'll get A as P, D and P inverse. Now, if you remember, the second part of the question was to find it A raised to the power 8.
Yes. Yes.
Right. So one way of doing this is you can multiply A 8 times. You can write A like this 8 times and you can multiply. So
Yes.
if you have time and you can do that, you can find the matrix A to the power 8, but that will not be a smart way to do it, right?
Yes. Yes. Yes.
So we will not do that. Instead, what we will do is we can write this as this form.
Hmm.
8 times. And what this will do is this will make an identity. Similarly,
Yes.
there will be another term, it will get multiplied with P inverse, that will be an identity. So ultimately what we will be left with is P D 8 times and again P inverse. And what that will do is P D raised power 8 and P inverse. Now you will ask me, okay, so I had to find A raised to the power 8. Now I have to find D raised to the power 8. Okay, how am I, like, what is the advantage of this? The advantage of this is D is a diagonal matrix. And
Hmm.
the 8th raised power of a diagonal matrix will be the 8th power of all the elements. So if I
Oh,
am not wrong, this was the matrix. So this
yes.
would be D raised to the power 8. So this is the advantage.
Yes. So there is no need to do. That means this system become a not costlier. This will become a quite cheap.
Quite,
That means
yeah. This will be easy to do, right?
yeah, easy. That means in the sense easy. Suppose higher calculation that is a costly and lower calculation that is a
Right.
easy. Okay.
If you are speaking about in terms of computer multiplication, yes.
Yes. In terms of computing, yes,
Right.
correct.
Right. In terms of computing resources, yes. Right.
Yeah, correct. Okay, good. Sir, actually, whenever I attend the session of the sir, so this type of things must be comes in our mind. Why we are finding this thing? Why we are finding this diagonalization?
Okay.
Because by this way we can reduce our computational task. So definitely, sir, explain each and everything. But this type of concept is learning after this type of discussion. So is
Okay.
there any way in a running time lecture so we can get directly it? Suppose sir would tell like this way, then we are really happy.
Okay.
But due to the
See,
constraint,
I
time constraint,
understand I understand your question. So just hear me out. So I don't decide the modality of this. And
no, actually, sir.
logistically speaking, see, those are pre-recorded lectures. This is a live session. These are two different things. But
Mhm.
you can post same questions to sir as well. So on the portal, you can ask the same questions to sir, and he will definitely answer. You just note down your questions and
No,
put them on the.
actually, one sir, I would like to say, in some other course, one of my friend had.
I cannot speak about other courses. I can speak
No,
only
no,
about this.
yes, actually, what answer we are getting, that's why I have to say it. Somebody asked like this way, sir, we are not understood this thing. So answer we are getting like this way. Ki this is the course of MTech and this is the course of PhD level. So you must have to do this thing. This must be learned by yourself. So that type of answer we are getting. That's why, yeah, that's why I will discuss with you. Sorry for that, but
That is again irrelevant. So I'll go back to this problem. You can probably ask your questions after the session is over. Okay. So let me finish the problems.
yeah, no problem, no problem.
Can you mute yourself, Jitendra? You can unmute while asking the questions.
Continue.
So now we have found out d raised to the power 8. We will just multiply that with, so to get a to the power 8, we will have to multiply p d raised power 8 and p inverse. This will be the matrix a raised to the power 8, and this is how we will be able to find powers of a matrix depending upon like the way we can diagonalize it, and then we can find the powers of a matrix. So next we will solve an example that does the singular value decomposition. So we will do singular value decomposition of this matrix. I think you have been taught in class how to do singular value decomposition. So first we will find this matrix. So it's a square matrix and it is symmetric as well. So if you interchange the A transpose, so this is a symmetric matrix. So if we change the row to column, column to row, it will be same. Now we have to find the eigenvalues of this matrix. So again, we'll have to find the characteristics equation. And then find the determinant of this matrix as 0. So the two eigenvalues of this matrix are 8 and 2. Now corresponding eigenvectors. So for lambda equal to 8, this will be so if we multiply any row, that will be the first and second row are almost identical if we multiply the second row with -1, like any linear combination. So this will be x1 equal to x2. So again, we put any value of x1, if just x2 is equal to that, the vector is an eigenvector corresponding to the eigenvalue 8. So we will find an orthogonal vector, orthonormal vector. So wait, we will find an unit vector. So lambda corresponding to 2x will be 1 by root 2, 1 by root 2 is 8. So this will be 8. Similarly, corresponding to 2, we can find as you can see, since it's a symmetric matrix, the eigenvectors are orthonormal or orthogonal. So orthonormal means if I take a dot product of these two vectors, that will be 0. Since this A transpose A is a symmetric matrix, the eigenvectors will be orthogonal. That is a property of the system. Now we will need to find U1, which will be in the direction of same as AV1. So then we will get as so if we just orthonormalize it, we will get as, so these two are similar. U1, U2 will be AV2, which will be 0, 1. Similarly, so the singular value decomposition will be of A, which is equal to 2, 2 minus 1, 1 will be these are the square root of the eigenvectors, eigenvalues, and then we'll have this vector. I'll write that here. So there is a singular value decomposition. Now the next example will be, so you have been taught about the permutation matrix in your previous week's lecture. I want to demonstrate to you how you can play around with permutation matrix and how powerful it can be given you know how to use it. This will be a small demonstration. So let me ask you a question. Find C cross 3 permutation matrix such that P cube is I, but P is not identity. Here I is the identity matrix of third order, 3 cross 3 identity matrix. How can you find this? So let me show you an example, like how can we find it. So let us see. Suppose this is a matrix, general matrix, and we will do simple row column operations on it. What does this mean? That we will interchange, like we will put row 3 as row 2, we'll put row 2 as row 1, and we will put row 1 as row 3. So if we do that, it will be G, H, I, then it will be A, B, C, D, A, F. Again, we will do the same operation. We will change the row 3 to row 2, row 3 as row 2, row 2 as row 1, row 1 as row 3, and this will be D, E, F, G, H, I, E, B, C. Again, we will do the same thing. We will change we will just change row 3 as row 2, row 2 as row 1, and row 1 as row 3. You can see we have done 3 steps and we are back to this. So we had started with a matrix, square 3 by 3 matrix, and by 3 sets of row column operation or permutation, we are back to the same equation. And see, I'm not doing any arithmetic operation with the rows. I'm just changing their positions, just permutation. So if I can find a matrix that can do this operation, because the operation is same, and multiply it on the left hand side, I will be able to get a system. I will be able to get a value of like this P can be a permutation matrix, which can be P cube is equal to I. So what I am doing is very simple. I am replacing row, the first row as third row, the second row as first row, and the third row as second row. So if you multiply this with this permutation matrix, you will get the row operation. And if you just take a cube of this, you will find that this is the identity matrix of third order, although this is not equal to I. So this is what I wanted to demonstrate to you. You can also find, also maybe you can do this as on your own. Try to find a 3 cross 3 permutation matrix such that P square is equal to I, although E not equal to I. So you can try this on your own. This is very similar to this. So I will give you an hint. Here we were interchanging 3 rows. You can choose any 2 rows, and first you change them, and second again you put them back in the same position. You will get a matrix P, and try to find a P by which you can do this, and this will be it. So thank you. That will be about today's lecture, that will have a tutorial hour, and you can ask if you have any questions right now.
Thank you, sir. I have right now no question. And thank you very much for explanation and clear the doubt.
Okay, thank you so much.
Thank you, sir. No questions from my side as well.
So let me see if there are any more questions.
Excuse me, sir.
Yes.
Sir, actually, I couldn't attend the last week's session. So is there any way I could get a recording of that meeting?
Yes, you will get a recording. You will get it will be uploaded to the portal very soon,
Okay, sir.
and there's no problem. All the lectures will be uploaded in due time.
Okay, sir.
The tutorial sessions, the lectures are already uploaded
Yes, sir.
week by week. This will be also uploaded. Don't worry about it.
Yes, sir. Thank you, sir. That will be great.
I'm assuming there are no more questions. All right. If I don't have any more questions, thank you for your attention. Have a good evening.